Right, we'll start a new chapter, electrochemistry. What is electrochemistry? Now, you might have heard redox reactions. So this is a reaction where reduction and oxidation are taking place simultaneously. It can be are classified as redox reactions. Now, uh, in chemistry, we know that there are transfer of electrons. So that transfer of electrons, the study of this transfer of electrons from one compound to the other, and the underlying principles governing it is studied under electrochemistry. Now, as we know, everywhere all the life processes occurs through redox reactions because either reduction or oxidation is taking place in any moment in time. Now, when we talk about this chapter, um, we know that the energy batteries are a source of energies, and in batteries, electrochemical reactions are taking place. So let's think about a typical battery, like a galvanic cell. Galvanic cell. Typically, a galvanic cell is where we have two figures. One is filled with zinc rod. The other one is tipped with copper, zinc rod and copper rod, and it's immersed inside a solution of zinc sulfate, and the other one is immersed in a solution of copper sulfate. Now, this solution is what we call as the electrolyte. The question is, when we connect these two terminals using a resistance such as a bulb, will there be generation, or will this bulb glow? That's the question. But until and unless we introduce something what we call as the salt bridge, then there will be no conduction of electricity between the two electrodes. These are the electrodes. This is the zinc electrode and the copper electrode. Now, the zinc the zinc electrode is where the oxidation is taking place. Zinc solid. And the copper electrode is where the reduction is taking place. So these two electrons gets transferred, and then plus, and you get copper solid. So this is cathode, and this is our anode. Anode, negative terminal, positive terminal. Just remember this T. It looks like this positive. And remember a freeze, an ox chasing a red cat. So oxidation, anode is where oxidation is taking place, and cathode is where reduction reaction is taking place and oxidizing of the red gas. That's a good mnemonic to go with. So this is a typical battery setup, and this salt bridge is composed of potassium chloride solution. And this salt bridge is introduced so that once you dip copper in copper sulfate solution, the copper ions, it starts to form copper ions, and it becomes saturated with the copper ions. So there will be no transfer of conductance of electrons. So this salt bridge acts as the carrier of electrons, extra electrons, in order to move the, or in order to conduct the current. So as we know in a battery, the electrons flow in this direction and the current flow in this, in the opposite direction. So this is a typical battery setup. And we have two types of batteries or cells, simply called cells. One is our electrochemical cells, and the other one is electrolytic cells. What is the difference? So this is a typical example of a galvanic cell. So this galvanic cells comes under electrochemical cells. Why? Because here, because of the spontaneous reaction redox process going on, it generates electricity. Flow of current is taking place. But in case of electrolytic cells, we have to supply external current or external energy in order to function these electrolytic cells. Suppose the perfect example is the batteries that you use at home for lighting up your household. We usually call it as inverter batteries. So in that typical battery, once you drain out, once electrochemical processes is complete, that means once the battery is fully discharged, you have to supply current in order to charge it. And during the charging process, it behaves as an electrolytic cell. So that is the basic difference between electrochemical cell and an electrolytic cell. Now let's talk about cell notation. So there is a convention of representing a cell. Suppose the galvanic cell, as I've mentioned, is the reaction between zinc and copper, giving us this. Now, how to represent it in the cell notation? So, by convention, we write the oxidation process or the anode process on the left side and the reduction process on the right hand side. So zinc solid is oxidized to glucose, and let's say we took 1 molar solution. So this is the phase boundary, means from solid to liquid, from solid to aqueous state, and then we put 2 more lines. This is our salt bridge, and then we represent the reduction, means copper plus 1 molar, and then the phase boundary for solid. So this is our anode, and then this is our cathode. So that's how we typically represent or write the cell notation for a particular redox process. So I hope you remember those. And suppose here we have both the anode and the cathode reactions. But suppose you want to know the potential of only one electrode. How do you do it? We need to find out the cell potential of individual electrodes. We have to use a reference, and that is called our reference cell. Reference ENCE, reference electrode. And that is where we use the standard hydrogen electrode. The standard hydrogen electrode is having a potential of 0 volts. So if you connect any of these two electrodes to this standard hydrogen electrode, then you'll be able to determine the potential of any of the electrodes. And we can relate the electrochemical process to thermodynamics using the Gibbs energy change, and the Gibbs energy change is related to thermodynamic parameters by this equation. So here n is the number of electrons transferred, during the reaction. F is our Faraday's constant, which has a value of 96 factorial coulombs per mole. And then this is our electrode potential. So if it is our standard Gibbs energy change, then we'll have the standard electrode potential for that particular cell. So this equation is very valuable for numerous calculations. So let's solve an example. We have been given the standard reduction potential of copper as 0.327 volts and oxidation negative 0.153 volts, and we are asked to calculate again the reduction potential of this copper. Now here we see that it's reduction process and it involves 2 electrons. Like copper plus 2 electrons will give us copper solid. And this is our first Gibbs energy change. In the second process, we have oxidation, which is giving us 1 electron. So this is our second Gibbs energy change. Now if we add this to Gibbs energy, then this cancels out, this electron cancels out, and the remaining is U plus 1 electron, giving us copper solid. So this is our final Gibbs energy change. So final Gibbs energy change is nothing but the addition of these two. So now we know that Gibbs energy change is equal to negative NFE. So you plug in these values because they have given us the reduction potential, the redox potential, and then this is a constant, and you know how many electrons has been transferred at each and it keeps energy change. In the first, we have two electron transferred, negative. We should not forget the negative. Twice F into 0.337 volts plus here only one electron, so negative F into negative 0.153 volts. So if you solve it, then you'll get around 0.521 volts. So our oops, finally change this one. So this corresponds to our reduction potential. So here is another example. You can try this one. And the catch here is it's in acidic medium, which means that in order to balance the redox reaction, you know what to use. You have to use a baton. Alright, in your mind. And I think you should arrive at around 1.69 volts. So if you can't solve it, you can ask me. Okay, so you try to study the difference between EMF and potential difference. It's given in your book. And then potential difference, yeah. And then you can also study the applications as well as the importance of standard hydrogen electrode. And then you also read the electrochemical series. What do you mean by electrochemical series? And this electrochemical series is nothing but the arrangement of different atoms with respect to hydrogen electrode, their potential difference in terms of oxidizing power and reduction power. So you try to read those things on your own. And now let's move on to the dependence of electrode and cell potentials on concentration. Different electrochemical cells, as we know, it's a redox process, it's a spontaneous process, and it depends on the concentration of the individual cells. So, and that dependence was or is incorporated in the Nernst equation. Nernst equation. So this is a beautiful equation, and this gives you the relation or the dependence of electrode and cell potentials on different concentrations. So we'll try to study that now. Okay, so the Nernst equation for electrode potential. Suppose Nernst equation. No, it's given in your book also. You can go through it. So for any reduction in electrons, get solid metal. So and this is a reversible process. So for this reaction, the Nernst equation, here reduction is equal to the standard reduction potential minus RT NF natural log of the so we can reduce reduce this by changing this natural log to the base, log to the base 10. Then we'll have 2.303 over NF natural log mn plus RT. And we can further reduce this by plugging in the value of the Faraday's constant. Reduction minus 0.059 over n RT log of m plus. So that is our final equation, or the Nernst equation, which suggests that for every transfer of, suppose the transfer of electron is 1, only one electron is transferred during the reaction, means it needs we get around 60 millivolts, 59, it's around about 60. So for one electron transfer we need 60 millivolts of energy. Now for hydrogen electrode, since we'll use only one electrode, and hydrogen electrode is a standard electrode, so okay, yes. So our Nernst equation will look like E naught minus 0.059 over 2, because there are 2 electrons involved, log of the pressure of the hydrogen gas at that particular temperature. The Nernst equation. So we'll try to work out some examples. So here is a question we are asked to calculate the redox potential of the hydrogen electrode. So the hydronium ion is equal to root over the concentration, which is root over 1.8 into 10 raised to the power minus 5 into concentration is 0.1 molar, which is nothing but this. So the value of hydronium ion is 1.8 into 10 raised to the power negative 6. So the reduction potential is nothing but since the reaction is involving 2 electrons, so the standard reduction potential is minus 0.059 over, we have 2 electron transfer, and the log of y r squared. So the standard reduction potential of hydrogen electrode is 0, so 0 minus 0.592 log of the pressure is given as 1 atmosphere, and this we have calculated. So it's root 2, so we'll just write the value directly, 6. So if you solve it, you get around negative 0.169 volts. Okay, here's a question. So you're asked to determine which has a strong oxidizing power. I suggest you take these assignments and homeworks seriously. You submit it on time, because this year I think we won't be having that many practicals. So I think your these homeworks and assignments will be part of your internal assessment. So I suggest you take these things seriously. So you submit it on time. We'll continue with Colroyd's law, this same chapter.